Hi, this is Gangadhar, lecturer in mathematics from Giraj Government College, Nizamabad. So now today's topic is BSC second year mathematics. So in the real analysis or convergent of series, infinite series, integral test and alternating series. So first, the statement of integral test is let f be a non-negative decreasing function on left closed 1 to infinity interval, then the series sigma f of n and the improper integral 1 to infinity f of x dx converges or diverges together. So it is the statement of integral test. So here sigma f of n and the improper integral 1 to infinity f of x dx are converge or diverge together. So if f is non-negative decreasing function on left closed 1 to infinity interval, so now proof of the theorem is, first the function f is decreasing, means we write integral k to k plus 1 f of x dx is less than or equal to f of k. Integral k to k plus 1 f of x dx is less than or equal to f of k. So this value also less than or equal to integral k minus 1 to k f of x dx. So applying this inequality for k equal to 2, 4, 2, 3, 4 so on values, then we get sigma. So 1 to n plus 1 f of x dx less than or equal to sigma k equal to 1 to n f of k less than or equal to f of 1 plus sigma 1 to n f of x dx. So the series converges if and only if the nth partial sum is convergent. So nth partial sequence is convergent means it is bounded. So we know every convergent sequence is bounded. So but we see from the inequality 5 that if the limit of the integral is finite, so then these partial sums are bounded. If the limit of the integral is infinite, then these partial sums are unbounded. So therefore we say that sigma f of n series and the improper integral 1 to infinity f of x dx are converge or diverge together. So now we will see one problem. Show that the series p test star, it is auxiliary series, sigma 1 by n power p equal to 1 by 1 power p plus 2 by 1 by 2 power p plus 1 by 3 power p plus so on plus 1 by n power p. So here this series is, we know, convergent if p greater than 1 and divergent if p less than or equal to 1. First case we will take p greater than 1, then f of x equal to 1 by x power p. So here p is positive, then 1 by x power p value also positive. So 1 by x power p means it is a decreasing series or decreasing function, continuous decreasing function, and integral 1 to x f of x dz value we will take 1 by p minus 1, integral 1 to infinity f of x dx value we will take 1 by p minus 1. The series converges by the integral test. Now the series converges by the integral test and the sum of the series is not generally 1 by p minus 1. So if p less than or equal to 0, then sum diverges by nth term test. So if 0 less than p less than 1, then 1 minus p greater than 0, and integral 1 to infinity 1 by x to the power p dx equal to that value we get infinity, means it is integral value does not exist, means series is divergent. If integral value exists, then series is convergent. So therefore p greater than 1, then sigma 1 by n power p series is convergent, and p less than 1, then sigma 1 by n power series is divergent. So now next problem. Test for convergence of sigma 1 by 2n plus 1 whole power whole cube, 2n plus 1 whole cube. So here f of x equal to 1 by 2x plus 1 whole cube, 1 by 2x plus 1 whole cube. Next we find integral 1 to infinity f of x dx value. So integral 1 to infinity f of x dx value exists, then we say that series is convergent. If that value does not exist, integral value does not exist, then we say that series is divergent. So now we find the integral value 1 to infinity 1 by 2x plus 1 whole cube dx. So that equal to 1 by x cube integration is minus 2 by 1 by x cube integration is minus 2 by x square minus 1 by 2x square. So 1 by x cube integration minus 1 by 2x square. So minus 1 by 2 into 1 by 2x plus 1 whole square into 2, and we apply limit n tends to infinity, that is x tends to infinity. Here limits 1 to infinity we write. So limit t tends to 1 to t, limit t tends to infinity 1 by 2t plus 1 whole square minus 1 means 1 by 3 square. So the here we apply the limit, then we get limit value 1 by 9. So 1 by 9 means it is existing value. So we say that the series sigma f of n converges by integral test. So now next problem. So determine the divergence or convergence of the series sigma 1 by n into log n. So here f of x value is f of n equal to 1 by n into log n. So f of x means 1 by x ln x. We find integral 2 to infinity 1 by x ln x dx, that equal to limit b tends to infinity integral 2 to b 1 by x ln x dx, or we say that t also. So now 1 by x into ln x integration value. So here it is f dash of x by f of x model, 1 by x by log x, f dash of x by f of x integration log f of x. So log of log x between the limits 2 to b. So now log of log b minus log of log 2. So log of log b value b tends to infinity means we get infinity minus something is infinity. So integral value infinity means given series is divergent. So if we get any value for integral, then we say that given series is convergent by integral test. So next example. So determine if the following series converges or diverges. So now sigma n square by n cube plus 1, sigma n square by n cube plus 1. So integral 0 to infinity f of x dx, x square by x cube plus 1, that equal to we write limit t tends to infinity integral 0 to t f of x dx. So x square, x cube derivative is 3x square. Here and divide and multiply with 3. Then we get f dash of x by f of x model. So f dash of x by f of x integration is log f of x, 1 by 3 into log of x cube plus 1. Between the limits 0 to t, we write x plus t and x plus 0. Then limit t tends to infinity 1 by 3 into log of t cube plus 1. So log of infinity, t tends to infinity means log of infinity value infinity. So total integration value we get infinity. So by integral test given series is, we say that divergent. So next problem. So sigma n equal to 2 to infinity 1 by 2n plus 1, 2n plus 7 whole cube. So integral 2 to infinity f of x dx equal to limit to t tends to infinity integral 2 to t f of x dx. So 1 by x cube integration minus 1 by 2x square. So minus 1 by 2 into, so 1 by 2x plus 7 whole square between the limits 2 to t. So we substitute x equal to t minus and x equal to 2. So overall limit we get 1 by 484. 1 by 484 means it is existing value. So we say that given series is convergent by integral test. So next, so one test, Cauchy's condensation test are also called condensation test. Cauchy's condensation test are also called condensation test. So now statement is, let sequence un be a decreasing sequence of positive terms, then sigma un converges if and only if sigma 2 power n u 2 power n series is convergent. So let sequence un be decreasing sequence of positive terms, then sigma un series convergent if and only if sigma 2 power n u 2 power n series convergent. So now example, so sigma n equal to infinite 1 by n into log n whole power 3 by 2. So here un value 1 by n into log n whole power 3 by 2 for n greater than or equal to 2. So first 1 by n into log n whole power 3 by 2. So here the values are n 1 by first n into log n whole power 3 by 2 is increasing sequence. So 1 by n into log n whole power 3 by 2 is decreasing sequence. So sequence un is decreasing. Next sigma 2 power n u 2 power n value we get sigma 1 by n power 3 by 2. Sigma 1 by n power 3 by 2. Here we apply p test. P equal to 3 by 2 greater than 1. So by p test sigma 2 power n u 2 power n series is convergent. So by condensation test sigma un series also convergent. So now next problem, the auxiliary series sigma n equal to 2 to infinity 1 by n into log n whole power p converges if p greater than 1 and diverges if p less than or equal to 1. So the series sigma 1 by n into log n whole power p, it is called auxiliary series. So this series is convergent if p greater than 1 and it is divergent if p less than or equal to 1. So now proof of the theorem or solution of the problem. First case, let p less than or equal to 0. So un value 1 by n into log n whole power p. So p is negative, p less than or equal to 0, then 1 by n into log n whole power p value greater than or equal to 1 by n. So for all n greater than or equal to 2. So here sigma 1 by n series is divergent by p test. So therefore by comparison test sigma un is divergence. Sigma un is divergence. So next p greater than 0. So here p is any real number means it is positive or negative or equal to 0. So three cases here we will take. In the first two cases p less than 0 and p equal to 0 series is divergent. Next p greater than 0 case. So p greater than 0, then un equal to 1 by n into log n whole power p. So it is positive, means sigma un is positive. sigma n is positive. So here n into log n whole power p is increasing sequence, then sequence un is decreasing, 1 by n into log n whole power p is decreasing. So sequence un is decreasing sequence. Next we find the value sigma 2 power n u2 power n. So that value we get sigma 1 by n power p. So that value we get sigma 1 by n power p. We apply p test. So by p test p greater than 1, then series sigma 1 by n power p is convergent, and p less than or equal to 1, then sigma 1 by n power p is divergent. So by condensation test p greater than 1, sigma 1 by n into log n whole power p is convergence, and p less than or equal to 1, then series is divergent. So some examples here. So sigma 1 by n into log n, so log n whole power 1, p value 1, then series divergent. Next sigma 1 by n into log n whole power 1 by 2, p value 1 by 2 less than 1, series divergent. Sigma 1 by n into log n whole power 3 by 2, so here p value 3 by 2 greater than 1, series convergent. Next p value 2, series convergent. So now next topic is alternating series. Alternating series. In the series, terms are alternately positive and negative. In the series, terms are alternately positive and negative. Then that series is called alternating series. In the series, terms are alternately positive and negative. Then that series is called alternating series. So a series whose terms are alternately positive and negative is called an alternating series. So it is the series we write u1 minus u2 plus u3 minus u4 plus so on, plus minus 1 to the power n minus 1 into un plus so on, minus 1 to the power n minus 1 into un plus so on. So where each un is positive or negative. So it is denoted by sigma n equal to 1 to infinity minus 1 to the power n minus 1 into un. So for example, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on. So in sigma notation, sigma n equal to 1 to infinity minus 1 to the power n minus 1 into 1 by n. Next example, 1 minus 2 by log 2 plus 3 by log 3 minus 4 by log 4 plus so on. So that equal to, we write 1 plus sigma. So we will take n equal to 2 to infinity minus 1 to the power n minus 1 into n by log n. So now convergence of alternating series. So convergence of alternating series, here we define one theorem, that is Leibniz theorem. Here we define one theorem, that is Leibniz theorem. So this theorem statement is, if un is sequence of positive terms, if sequence un is sequence of positive terms such that u1 so if sequence un is sequence of positive terms such that u1 greater than or equal to u2 greater than or equal to so on, un greater than or equal to un plus 1 so on greater than or equal 0, and limit un equal to 0, limit un equal to 0, then we say that alternating series is convergent. Then we say that alternating series is convergent. So now proof of the theorem. first the nth partial sum of the series. Nth partial sum of the series we will take Sn equal to sigma minus 1 to the power n plus 1 un. So sigma minus 1 to the power n plus 1 un. So here series is convergent means limit exists. So satisfies mod s minus sn less than or equal to un for all n. So we need to show that the sequence Sn converges. We need to show that nth partial sum of the series is convergent. Then we say that given series is convergent. So here we define nth partial sum is Sn equal to. So now thus we define subsequences of Sn are S2n. So the subsequence of SNR we will take S2n and S2n minus 1. So these two are subsequences of Sn. S2n sequence S2n and the sequence S2n minus 1 are two subsequences of sequence Sn, and their definitions S2n plus 2 minus S2n equal to minus 1. This way we define. So now we claim S2m less than or equal to S2n plus 1 for all m comma n belongs to n. First note that S2n less than or equal to S2n plus 1 for all n. So because S2n plus 1 minus S2n equal to U2n plus 1 greater than or equal 0. So if m less than or equal to n, then from 1 S2m less than or equal to S2n less than or equal to S2n plus 1. Next, if m greater than or equal to n, then from 1 S2n greater than or equal to S2m plus 1 greater than or equal to S2m. So we see that sequence S2n is increasing subsequence of sequence Sn bounded above by each odd partial sum. So by each odd partial sum, and S2n minus 1 is decreasing subsequence of sequence Sn bounded below by each even partial sum, and these subsequences are convergence. So t minus s equal to limit n tends to infinity S2n plus 1 minus limit n tends to infinity S2n. So that equal to 0. So implies s equal to t. So it follows that limit Sn equal to s and sequence Sn converges to s. Therefore given alternating series is convergent. So now we will see some problems here on alternating series. So first 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 show that the series is convergent. First we write summation or sigma notation. So sigma n equal to 1 to infinity minus 1 to the power n minus 1 into 1 by n. So it is a alternate plus minus terms are there, means it is alternating series. So here we apply Leibniz test. So Leibniz test statement is first un is decreasing and limit un equals 0. Then we say that given alternating series is convergent. First un value 1 by n. So 1 by n means the values of un are 1, 1 by 2, 1 by 3, so on values. So we say that it is decreasing. So un greater than or equal to un greater than un plus 1 means sequence un is decreasing, and limit n tends to infinity un equal to limit n tends to infinity un equal to limit n tends to infinity 1 by n, that equal to 0. So here sequence un is decreasing and limit value 0. So by Leibniz test we say that given alternating series is convergent. So in the next example, so sigma minus 1 to the power n minus 1 into n by 2n minus 1, n by 2n minus 1. First un value, un equal to n by 2n minus 1. Next un minus un plus 1 is greater than 0, means un greater than un plus 1. Un greater than un plus 1 means sequence un is decreasing. Next we find limit un. So that limit un value we get 1 by 2. Limit un value we get 1 by 2, it is not equal to 0. So therefore by Leibniz test we say that given alternating series is not convergent, means it is divergent. So next problem, sigma minus 1 to the power n by n factorial. So un equal to 1 by n factorial. So n less than n plus 1, then 1 by n greater than 1 by n plus 1. Apply both side factorial. 1 by n plus 1 factorial greater than 1 by n factorial greater than 1 by n plus 1 factorial. So that implies un greater than un plus 1. Un greater than un plus 1 means given series sequence un is decreasing sequence, and limit un equal to limit 1 by n factorial that equal to 0. So therefore by Leibniz test sigma alternating series is convergent. Next problem, 1 by 1 into 2 minus 1 by 3 into 4 plus 1 by 5 into 6 minus 1 by 7 to 8 plus so on. So here the nth term is 1 by 2n minus 1 into 2n. 1 by 2n minus 1 into 2n. So un. So un is decreasing. Un is decreasing. And limit un equal to 0. Limit un equals 0. So by Leibniz test, the given series is convergent. So now some definitions are there here. So the definitions are absolute convergence. Absolute convergence. If sigma mod un series is convergent, then sigma n is called absolute convergent. So next definition, conditional convergent. If sigma mod un series is divergent, then sigma n is called conditional convergent. So here sigma mod un is convergent, then we say that given series is absolute convergence. If sigma mod un series is divergent, then we say that given series is conditional convergent. So now one problem. So test the convergence of the series sigma x to the power n by n. So here un equal to sigma x to the power n by n. So here we apply either nth root test or ratio test also here we apply. So by ratio test, un value 1 by n, un value 1 by n. So un plus 1 by un equal to x to the power n by n. So we find the limit of un plus 1 by un. So that limit value we get x. Limit value we get x, say mod x. So by ratio test, mod x less than 1, series convergent. Mod x greater than 1, series divergent. So when x equal to minus 1, then sigma n equal to sigma minus 1 to the power n by n is convergent. When x equal to 1, series divergent. So next problem. So un equal to sigma n equal to sigma x to the power n by n factorial. Sigma x to the power n by n factorial. So in the series n factorial term is there. Then we apply ratio test. D'Alembert ratio test. So for ratio test, first we write un value and un plus 1 value. Next we find limit of un plus 1 by un. That limit value less than 1, then we say that series is convergent. Limit value greater than 1, then we say that series is divergent. So now we find the limit value mod x by n plus 1. So this here mod x by n plus 1 limit value 0. N tends to infinity 1 by n 0. 0 less than 1. So 0 less than 1 means given series is convergent. And sigma mod un is convergent. Then we say that given series is absolute convergence for all x belongs to R. So next problem, sigma minus 1 to the power n minus 1 x to the power n by n. So it is convergence for minus 1 less than x, x value lies between minus 1 to 1. So if x equal to 1, then sigma minus 1 to the power n minus 1 into 1 by n. So we know that series is convergent. If x value lies between minus 1 to 1, then mod x less than 1. Mod x less than 1. Here we find mod un. So mod un and mod un plus 1, apply ratio test. Mod un plus 1 by un equal to mod x by 1 plus 1 by n factorial. That limit value we get mod x. So here by ratio test, sigma mod un is convergent for mod x less than 1. So therefore given series is convergent for minus 1 less than x less than or equal to 1. So now prove that sigma minus 1 to the power n sin 1 by n is not absolutely convergent. So first series sigma n equal to sigma minus 1 to the power n sin 1 by n. So we will take Vn equal to, choose Vn equal to sin 1 by n, and 1 by n greater than 1 by n plus 1, sin 1 by n greater than sin 1 by n plus 1, Vn greater than Vn plus 1, and limit Vn equal to 0. So limit Vn equal to 0, by Leibniz test sigma Vn is convergent. So next sigma mod un. Sigma mod un means sigma mod sin 1 by n. So sigma mod sin 1 by n. So we find limit mod un. So that value we get 1, and 1 not equals 0, limit value not equals 0. So by comparison test, sigma mod un is divergent. Sigma mod un is divergent, since here sigma an equals sigma 1 by n is divergent. So here we apply limit comparison test un by vn model. So limit value not equal 0, but sigma vn equal to sigma 1 by n is divergent. So sigma mod un is divergent, therefore sigma vn is conditional convergent. So now sigma minus 1 to the power n plus 1 into n by n square plus 1. So un equal to minus 1 to the power n plus 1 by n into n square plus 1. So first we find the limit un. So limit value we get 0. So by Leibniz test, alternating series convergent. Next we will take mod un. Mod un equal to sigma n by n square plus 1. Sigma 1 by n square plus 1. So here we apply limit comparison test. We choose Vn equal to 1 by n. We choose Vn equal to 1 by n, and we find the limit value mod un by Vn. So that limit value we get 1. But here sigma Vn equal to sigma 1 by n is divergent. Sigma Vn equal to sigma 1 by n is divergent. So by comparison test, sigma mod un divergent. Sigma mod un divergent, then we say that given series is conditional convergent. Given series is conditional convergent. So now sigma minus 1 to the power n plus 1 into root n plus 1 minus root n. Root n plus 1 minus root n. So here given function is rational function, so we rationalize the numerator value. So then we get un by vn value. So un rationalize that function, then we get 1 by root n plus 1 plus root n. So here given series is sigma un equal to sigma minus 1 to the power n plus 1 into 1 by root n plus 1 plus root n. So un, sequence un is decreasing, and its limit value 0. 1 by root n plus 1 plus root n means limit value 0. So by Leibniz test, given alternating series is convergent. Next, sigma mod un value 1 by root n plus 1 plus root n. So here we apply limit comparison test. So we choose vn equal to 1 by root n is common. So 1 by root n. Sigma 1 by root n is divergent by p test. So now sigma mod un series is divergent. So therefore given alternating series is conditional convergent. So thank you. Namaskar.